In this video, we're going to be looking at solving inequalities, and for the sake of simplicity, I'm just going to stick with linear inequalities in this video. So, hopefully at this point you're familiar with equations and how to solve for variables, but if not, you can certainly take a look at some of my other videos. So, to start off with, an inequality should be treated exactly the same way as an equation would be treated, except for two differences. The first difference is the obvious difference that we don't have an equal sign in inequalities because they're not equal, they're inequalities. And the second difference is whenever we divide or multiply, we have to switch our sign around. And I'll show you what I mean by that in a moment. So to start off with, I'm just going to give you an example of x plus 5 is greater than 7. So to solve this inequality for x, we would treat it exactly the same as we would an equation, and we would just subtract the 5 from both sides, leaving us with x is greater than 7 minus 5, which is 2. And so essentially what this means is x can be any value in existence as long as it is bigger than 2. So we could plug 3 back in for x, or 4, or 5, or 10 million, and it would always give us a true statement. For example, let's say we had 3. 3 is bigger than 2. If we plug 3 back into this inequality here, it would get 3 plus 5, which is 8, and 8 is greater than 7. So inequalities always work when you plug it back in, or else you've done something wrong. So that's essentially how this works. So now let's take another example of 3x plus 2 is equal to or less than 11. So once again, we're going to subtract our 2 from both sides, and we'll end up with 3x is equal to or less than 11 minus 2, which is 9. And then, just like with an equation, we have to get our variable by itself. So we're going to divide by 3 on both sides. That'll cancel and give us x is equal to or less than 3. So again, here we could plug in 3 or 4 or 5, any number that is equal to 3 or less than 3, 3 or 2 or 1, and so on. Any number is equal to or less than 3 in for x, and it would be a true statement. But if we plugged in anything that is greater than 3, we would get not a true statement. For example, let's take 4 and plug it back in. I just kind of want to show you that it works this way. So we'll plug 4 back into this equation here. This inequality here. So 3 times 4 plus 2 is equal to or less than 11. So 3 times 4 is equal to 12. 12 plus 2 is equal to 15. And 15 is not equal to or less than 11. So there's an example of trying to plug in a number that is not fitting into this criteria here that we've solved for. So that's just how inequalities work. So here's another example of negative 5x plus 7 is equal to or greater than 17. Now this is going to be a little bit different, and this is where the switching the signs around is going to come into play now. So initially we're just going to treat it exactly like we would in the equation. So we're going to subtract 7 from both sides, giving us negative 5x is equal to or greater than 17 minus 7, which is 10. Now we're going to do what we would normally do to get this x by itself. However, when we do that, we're going to be dividing by negative 5 on both sides. And negative 5 is obviously it's a negative number. And as I said before, when we divide or multiply by a negative number, we have to switch the signs around. So what's going to happen is we're going to get x is equal to or less than negative 2, rather than equal to or greater than, because we had to switch this sign around. So one more example of, let's take x over negative 5 plus 13 is greater than 28. So now, again, treat it like a regular equation. We're going to subtract 13 from both sides and get x over negative 5 is greater than 28 minus 13, which is equal to 15. So now we have x over negative 5 on the left side, so now we have to multiply by negative 5 to get the x by itself. So times negative 5 times negative 5, and our negative 5s will cancel, and just as we did before, we've multiplied now, rather than divided by, a negative number. So having multiplied by a negative number, we have to switch our sign around and give us 15 times negative 5, which will give us negative 75. So x is less than negative 75. So actually, let me just give you one more example of solving inequalities that's a little bit more complicated than what I've been giving you, because really all these examples that I've shown you are pretty much two-step problems. So let me just throw one little more complicated problem in there just to solidify things a little bit better than I have. So let's take the inequality negative 7x plus 13 is equal to or greater than negative 5x minus 2. So this is just a couple more steps to demonstrate things a little bit more clearly. So let's first off add 2 to both sides, giving us negative 7x plus 15 is equal to or greater than negative 5x. So now let's get our x's on one side by adding 7x to both sides, which will leave us with 15 is equal to or greater than negative 5x plus 7x, which is equal to 2x. So now all we have to do is divide by 2 on both sides, which will give us 15 halves is equal to or greater than x. And you'll notice that we didn't have to switch our sign around on this one, even though we had to add, negative x's and such. We had negative x's all over the place, but it does not have an impact on the direction of the sign, because we didn't ever have to divide or multiply by a negative number. So that is how you would go about solving inequalities.